What I want to have a look at now is how tectonic plates move, followed by a bunch of case studies. If you want to have a look at this video, it's in the description. It's a little bit dense to do with academic language, but it's a really good one, and it's one of the first ones that I've seen describing plate motion properly, which is pretty disappointing because the whole convection currents thing is everywhere. And it's quite funny because at the start of this particular video, comments that old textbooks have have reference to convection currents driving plate tectonics, and I'm just like, man, it's not old textbooks, it's current textbooks and most teachers. So it's pretty frustrating, but this is life. It's something I've been trying to change. Look, they're slowly getting it right, but anyway. So gravity is the main driver, not heat loss. If it was heat loss, you'd get nice big convection cells and all that sort of stuff through the mantle, but that's not what's happening. Gravity is the main driver. So what we have is when dense oceanic crust and relatively buoyant continental crust collide with each other, we get those subduction zones. And as the oceanic crust dives into the mantle, it pulls the whole plate along behind it. Gravity also drives pushing away from a mid-ocean ridge. So essentially at a mid-ocean ridge, it's a mountain range, and while the slope of the mountain range is very gentle, over about 80 million years, the size of the oceanic crust changes dramatically. So we're talking at the ridge maybe 3 kilometers below sea level, and then about 80 million years later, as you've gone down the slope, it's about 5 or 6 kilometers below sea level. So there's a relatively large drop. Now what that means is, as we know, if something's on a mountain, it has more gravitational potential energy. Yeah, and that can turn into kinetic energy as it moves down a slope. And that's happening to the rocks in the slope as well. So the rocks that are high up near the mid-ocean ridge, they've got gravitational potential energy, and they want to go down the slope that's right next to them. And what that does is that's called ridge push. So we're getting a little bit of pushing there at the mid-ocean ridge. So we've just gone back to this slide again because of the case studies we're about to have a look at. So we're looking at convergent plate boundaries, subduction zones, and regions of mountain building. Those two things we're going to look at. So the first place we're going is to the Mariana Trench. That video is a link to that in the description. So the Mariana Trench is interesting. Like at a subduction zone, you kind of get a trench right there anyway, at just that little corner bit where the oceanic plate subducts under the continental. But what we can see here, and the Mariana Trench is located right here, Challenger Deep is the deepest part, we can see that we've got an bit of oceanic crust subducting under other oceanic crust. So it already starts a fair way down, and so we can probably easily imagine, well, why it's so deep. It's an interesting situation here. We actually have this plate subducting under that plate, and that plate subducting under that plate. So we get like a triple point over here at Japan. We'll talk about that at another time. So Mariana Trench is very, very deep, so 11 kilometers. Average ocean depth is only 4 kilometers. So that tells you it's pretty damn deep, and it's 2,500 kilometers long. The Himalayas are a similar sort of situation in that there's convergence going on, but what we have actually is we did have a subduction zone. So just a standard subduction zone with oceanic lithosphere subducting under continental crust. So 60 million years ago, then 40 to 50 million years ago, they actually collided. So this bit of land that was being pulled over to Eurasia, so this Indian plate pulling over to Eurasia because of the subduction zone, they actually collide. However, the subduction zone keeps going. So that force of the subducting slope keeps going, and is actually enough to get these continents pushing into each other. Now when they push into each other, well, neither's going to really subduct, so there's only really one possibility, and that's when we get thrusting, so it's coming upwards. And as it comes upwards, we get an erosion as well. But what we can see that we have over here is we have sort of a plateau building up, till eventually, right on the edge 10 to 20 million years ago, we have the Himalayas really being thrust up quite high. At the moment, the Himalayas are still growing by a couple of centimeters a year. What's happening there is that Erosion, so the erosion of the mountain range is reducing it. However, the uplift from the collision is still winning. So the Himalayas are still going up. So we can see the continental movement here. So we got India moving until eventually it collided. India's joined to Australia over here somewhere, down to the bottom right. So I quite like this little video. It's taking us to the location. Whoever made it, good on you. So we can see what was in those diagrams before. So we can see the oceanic lithosphere subducting. We are getting some volcanism over here. Then we're getting some accretion through here. So this is starting to build mountains. At the top of Mount Everest, there are fossils. So it's all sedimentary rock up there. So it's this stuff which eventually gets pushed up. Indian plate collides. Okay, that's coming back, it's got to tell us. And it's eventually this one, because weathering and erosion must happen over here. Okay, so it's all sedimentary rock. So when we have convergence, we have volcanoes, because essentially most convergence is subduction. Very few locations, like the Himalayas was over there, that are just mountain building. So all the way around here we have subduction zones, and when we have subduction zones, we have volcanoes because of that subduction. Hundreds and hundreds of kilometers of them. Thousands of kilometers through here. We have a couple of anomalies just kind of in the middle of nowhere. And so this is along a mid-ocean ridge, we've got some there. But this is the Pacific Ring of Fire. Goes all the way around.